have been funded by many funding agencies, over $10 million. A research project since 92, 93 I joined our department. So as you can see is basically from Navy, Air Force, Army, NASA, JPL, Department of Energy, DOD, Department of Defense, National Science Foundation, DARPA, also companies like Trex Enterprises, Nanomaterials, Northrop Grumman, Allied Signals, Goodman Technology, Advanced Silicon Carbide Materials, Applied Research Lab. Dr. Tiwari gave my background, and so I won't spend too much time here. So basically, I graduated from University of Delaware Center for Composite Material, PhD in 92, joined our department. And then I got promoted to full professor in 2003 with tenure, and I've been ABET chair, also graduate chair of the department, 2006, 2009, and then also served as the department chair from 2009 to 2017. I developed 3 laboratories: Advanced Materials Manufacturing Laboratory, Intelligent Composite Materials Laboratory, Hawaii Nanotechnology Renewable Energy Laboratory, and I mentioned my funding agency, over $10 million research fund. I think Dr. Tiwari mentioned some of these. I have over 170 publications. I have a number of postdocs, PhD students, masters and bachelors, 7 postdocs, 11 PhD students, 33 master, 44 bachelor's students. So as those not mentioned, but Dr. Tiwari, I just point those out. I'm a Boeing Delaware Faculty Fellow, 1999, also Associate Editor of Journal of Thermoplastic Composite Materials. Dr. Tiwari mentioned about Guinness Book of World Record for the creation of world's smallest nano brush. I hold 5 patents and then 5 other pending. Then with my student, we won the national championship for the human power vehicle in 95, 97. And I have a number of awards from University of Delaware Center for Composite Materials and DuPont at the time of my PhD. So the topic of my presentation is overview of nanotechnology application in structures, composite, nanocomposite, renewable energy. So the summary of my talk basically condenses in these 4 technologies I have here. First, I call Nanoresin Technology, and I'll then briefly explain each technology. So Nanoresin Technology, meaning putting a functionalized carbon nanotube or graphene inside the polymer to improve the property of the polymers, primarily changing it from a brittle, let's say in terms of thermosets, from brittle to a tough polymer. And then next is a nanoforest, where we grow carbon nanotube on the surface of the fabric, then impregnate it with the resin and make laminates. This way, we improve interlaminar property, where normally is filled by matrix, but now we put nanoforest on it to improve interlaminar property, as well as make a 2D composite, a 2-dimensional composite into 3-dimensional composites. Next, we also develop world's smallest multifunctional nano brush that I briefly explained those. And some of these applications in renewable energy I'll explain, including wind turbines and also polymer exchange membrane fuel cells, and that I'll explain in terms of improvement of catalyst layers and gas diffusion layers. And finally, the 5th technology is the Nanopaste technology, where we invented what we call a Nanopaste ceramics-based composite, which is basically has a pre-ceramic polymer with embedded nanoparticles that can be printed, 3D printed. Like as you can see, this was like extruded. And then using this paste, we can do either 3D printing or molding to make structural parts. As you can see, these are space telescope structural parts, or optical parts. So we use this paste to make like mirrors, as you can see here. Okay, I'll go and explain this more in details. I have an 11-step overview of my presentation, but I won't probably get time to get all of this in details. So I'll go through basic in Nanoresin technology, Nanoforest technology, application of Nanoresin, Nanoforest in renewable energy, and then I'll talk about Nanopaste and some of the modelings we have done in nanotechnology. So first, Nanoresin. So we use, here we use nanoparticles inside the epoxy system to improve the properties. We can also use, we also use the CNTs, covered nanotube, and GNS, that is graphene nanosheets. We functionalize them and put it in the thermoset to improve the properties. So basically, with this inclusion of functionalized covered nanotube or graphene, we and that is less than 1% inclusion. That's the advantage of our technology patent. It's a small amount of nanomaterials you put, albeit functionalized, and you get large property improvement. For example, here you say viscosity doesn't change. You need that for processing. Class transition doesn't change. Modulus doesn't change much. Strength, but the strength to failure increases by 100%. Toughness increases by 200%. Damping increases by 300%. So in the landmark publication we had in the advanced functional materials, we showed that the very small amount of like up to 0.4%. Functionalized graphene, we can improve the property of fracture toughness by about twice of what exists without it. So here we show the functionalized graphene that we created in here, and that's shown as a TEM, and the process is given here that we started from a graphene oxide, which has a hydroxyl and carboxyl group, and then we functionalize it with MDI group, so you get this GONCO structure, molecular structure like that, and then we functionalize it with an amino group, and then eventually we get a graphene with the amino group functionalization that worked the best for the nanoresin that we had. We also introduced a coalescence microcrack mechanism, and then we explained that behavior of the nanocomposite, why it does what it does. That is the low percentage range that we discovered, and we filed for a patent and also published in this journal, Journal of Advanced Functional Materials, 2015. It shows that the very low loading of functionalized graphene, namely here 0.4%, you get close to twice fracture toughness improvement. But then interestingly, as you increase the inclusion, then the property drops, and then it increases again. So we introduced this coalescence microcrack mechanism that at low percentage, the functionalized graphene are well dispersed. So gradually, as you increase it, this toughness increases because it has effect on the surrounding areas as you increase the graphene. So when you get to a threshold, in this case 0.04%, then beyond that, those functionalized graphene will get close to each other. So the coalescence in this sense, and then they don't have that effect, so it's kind of an agglomeration, so the property drops. And this happens because of the larger inclusion and also van der Waals forces. But then when we change the mechanism from this well-dispersed nanomaterials to this coalescence, when the property drops, then the further increase of nanomaterials will still increase the property. The reason is that the crack will go through more nanomaterials. So this we introduced in this journal, this microcracks coalescence mechanism. So application of nanoresin is basically anywhere you use composite materials. We also use a nail polish to get improvement in performance. You can use this nanoresin technology also in ceramics. So pre-ceramic polymer you can use with continuous fiber. We call it CFCC, continuous fiber ceramic composites. So this yellow represents pre-ceramic polymer, black represents fibers. So this is CFCC without nanoparticles, but we can put nanoparticles in it and improve the property. So we showed that when we use different nanoparticles named here, titanium oxide, yttrium oxide, zinc oxide, carbon, and silicon carbide, so you get a property improvement. The open bars are plane infiltration, and then solid bars are nanoparticles. It means this is a PIP technique, polymer infiltration pyrolysis technique, that you should pyrolyze a number of times to increase the density. So that's the PIP polymer. We are saying that whether you should have nanoparticles or not, that's why we showed here. We showed that certain nanoparticles perform the best, for example, yttrium oxide. And then we pick that, increase the property from 10%, 15% to 20%. And we showed that as you increase the percentage of nanoparticles, they agglomerate and then they behave like a microparticle. They no longer improve the property. For example, 20%, you see here all the properties drop. Whereas at 5%, property improves both in the plane infiltration and then solid infiltration. But as you increase the percentage, then it's better to only start with 15% nanoparticle as the first time, and then subsequent infiltration should be plane infiltration to get up to 35% strength enhancement for nanoceramics, ceramic nanocomposites. So these are application of high temperature structural application for nanoceramic. So next technology is Nanoforest. Nanoforest is that we grow carbon nanotube on the surface of the fabric, so that way the problem is that if you don't have anything in between the layers, you just have matrix that grows. You don't have fibers. So we grew carbon nanotube in between so that we prevent or delay crack initiation and crack growth. So people have been working with knitting, stitching, and also braiding to solve that problem, but these have associated problem. For example, this knitting increases through the thickness property by 20%, but drops implant property by around 15%. So you give some, you take some. In this case, also for braiding, you see the fibers are not orthogonal, which is normally a designer use orthogonal fibers. And also, if you use thicker laminate, you still have to put a number of these together. You get interlaminar issue, which is a resin rich. In doing so, we first grew carbon nanotube on the surface of the fiber, and this way we created world's smallest multifunctional brush. We published in Nature Materials in 2005, and then we received the Guinness Book of World Record for the creation of multifunctional world, the smallest multifunctional nano brush. So we have a control on the growth of nano brush. You see, we have a different variety of nano brush. We can even improve the adhesion of the nanotube to the stem of the brush by annealing, so double the increase, double the shear strength of attachment of the carbon nanotube to the stem of the brush. So there are many applications, this nano cleaning, micromotor, nanomotor, electronic switch, and then cleaning inside microcapillary, that's medical application. Also, you can functionalize the brush with, say, a pyrene system, and that will attract harmful materials, ions in the industrial waste water, like mercury and silver and cadmium. This is the size of nano brush compared to a penny. So those are small, our carbon nanotube, this is the stem of it. So we go back to Nanoforest. So we published this in Nature Materials in 2006 and won the Best Paper Award in the ASME Aerospace Division in application of materials mechanics. So here, as received fabric, here we have Nanoforest on it. And here, as received, here we have Nanoforest on it. This is as received, this is Nanoforest. Even after fracture, carbon nanotube are attached. So we improve the property in many different areas like fracture toughness, mode 1, mode 2, damping, coefficient of thermal expansion, thermal conductivity, electrical conductivity, in-plane modulus, strength and toughness. You see all of them improve like 4 times, 6 times in different areas. For example, fracture toughness improves 4.5 times, damping 6 times, electrical conductivity is 1.5, and then huge thermal conductivity. Huge electrical conductivity because through the thickness, epoxy is not conductive. We put in carbon nanotube, it becomes conductive. Again, modulus, flexure modulus, the strength and also flexure toughness improves. So that we applied that also to ceramics. Also in ceramics, we get 40% improvement in flexure strength and 110% improvement in toughness for a ceramic composite. These are ceramics. So as I mentioned, 40% improvement in flexure and 114% improvement in toughness. Also, they have a close to zero coefficient of thermal expansion that has application in a space. So I showed, for example, regular materials, copper, aluminum, steel, they have positive coefficient of thermal expansion, CNT, GNS, they have negative coefficient of thermal expansion. We also created Nanoforest on the substrate, removed it and interleaved in composites. We call it Nanoforest 2. This we published in Science in 2005, and that showed other applications. So this is Nanobrush, Nanoforest, we call it Nanoforest 1. This is Nanoforest 2, we created and then remove it and interleave it in composite. So these are application of Nanoforest. Anywhere you use composite, you can basically use this. Application in energy is in the wind turbine blades that normally wind turbine have power related to R squared. This is the circle that created by the blade turning, but the weight is R cubed. So as you increase the weight of the blade, the length of the blade, to get more power, weight increases. So this is the sequential history of every 10 years, the radius of the, the diameter of the this swept area of the wind turbine doubles. But at some point, this reaches the limit because after that, due to weight, it will break. So we are proposing to use Nanoresin Nanoforest here to improve the property. Also, application to there is a fuel cell. And in fuel cell, you have a Nafion, the proton exchange membrane is here. Then you have a catalyst layer, this green, and then these two parts are gas diffusion layer. So we showed that we can improve the performance of catalyst layer by using like a Nanoresin technology. We put platinum nanoparticles on bed of carbon nanotube. This another researchers, they have 40% saving in nanoparticles, but performance was the same as without. So we had 60%. We use less platinum. So we had 60% saving in platinum, but we have 10% improvement. Also, we use Nanoforest technology for gas diffusion layer, and we got, again, 10% improvement performance of fuel cell, while saving on the moisture production, etc., because carbon nanotube are hydrophobic and they repel the moisture. So that's the improve of fuel cell. Also, people use P3HT and P3OT for solar cell, polymer solar cell. So we use carbon nanotube and graphene to improve the performance of solar cell using nanotechnology. Here's the nanocell, nano-fuel cell test station, nano-solar cell test station. Also, you can use nanomaterials in batteries, supercapacitor. The main idea is that on the cathode side, when you store the ion, when you charge it, if you have larger surface, you can store more ion, and then that way you increase the capacity of the batteries and supercapacitor. Now, carbon nanotube and graphene have a much larger surface to volume ratio, so they have potential to increase the battery energy density and so on. So last technology is Nanopaste, where we created, as I said, pre-ceramic polymer with nanoparticles in it, so we can print it, both print it and mold it to create a structural part as well as optical part. These are for a space application. So that's, you see, the paste. We also did some modeling. I want to go through it. I'm running out of time. So I just quickly show you, we did modeling for development, the modeling for effective coefficient of thermal expansion, and also thermoconductivity, electrical conductivity for both carbon nanotube and graphene. Basic fundamental modeling for either carbon nanotube and also for the graphene. This is modeling that. So I said we had a paper on chirality dependence of CTE, coefficient of thermal expansion for single wall carbon nanotube, and also chirality dependence of mechanical properties. Here we show different organization of the carbon nanotube, armchair here chiral. So those are the two papers that I mentioned, and also some applications. We modeled the effective modulus of the single wall carbon nanotube using asymptotic homogenization. This is an analytical solution. And then we compared that with finite element analysis for different chiralities. And then the result was very close. So in the finite element, in analytical, we get 1 terapascal for modulus, which is this line. But in the finite element, depending on chirality, so when you have pulling on a zigzag closer line, you get higher, slightly higher, and then you come to armchair, and then you repeat because it's a 30 degrees repeatability. See, this is hexagonal. So every 30 degrees, it just is periodic, it goes back. So it is a zigzag, armchair zigzag, but it oscillates around that 1 terapascal. So we had a very close approximation or the result between analytical solution and finite element. Here again, we modeled the just one as a combined. Here the black is a single wall carbon nanotube. You fill it with matrix inside and outside. So we had an analytical solution to find effective property, modulus, and Poisson's ratio. Also finite element that the results were very close, as you can see here. So here I have the list of publication for different papers that I mentioned to you. I'm running out of time. I just flash quickly the facilities we have. This is a precision weight measurement, magnetic stirrer, sonicator for dispersion of nanomaterials, spin coder, chemical vapor deposition furnaces. This is a small one we have. This is a larger one we fabricated in-house. This is a hot press. This is a autoclave. This is a high temperature furnace for ceramic processing, and then we do testing with the Instron machine. And we have other, like we have glog box and dual mixer and etc. So I've worked on many conferences. I just want to mention one. I don't want to take much time, and that is I worked with some of my colleagues to have the first multifunctional nanocomposite international conference hosted by ASME in Honolulu in 2006, and then after that they repeated that many times. Okay, we also received recognition in the Nanoforest, Nanobush and Nanoforest work we did, like BBC, National Geographic, ABC, MSNBC, CBS, USA Today, Fox News, Las Vegas. This is a local news, Washington News, and this is a local news, Hawaii, China Daily, India Daily, and others. And then those are for Nanobush, for Nanoforest, also Materials Today, Net Composite, Nanotechnology, and Science Daily, A to Z Nanotechnology, A to Z Materials. So here I showed many other applications I showed during my presentation of different technologies we had. I leave you with Arthur Clarke's statement of any sufficiently advanced technologies in this field.